Hi, good evening, everyone. Welcome to this BoF on cameras, which is about cameras on Linux. So my name is Karthik Poduval. I've been working in general about 19, 20 years of experience, most of it on cameras. I work with Amazon Lab126, where me along with my team, we work on doing camera software stacks for various Amazon products. Prior to that, I used to work with Samsung Electronics on smartphones, again, on cameras. So we'd like to keep this as interactive, so if anyone has anything to share, please. There's a mic going around, so I think two of my colleagues are also here. They're helping with passing the mic around, so if anyone wants to interrupt and have some thoughts to share or questions, please do so. I have prepared a slide deck so that we have a couple of things to go over. And in terms of, I'm not much of a contributor on Linux myself, but I've been using Linux for a long time. I've also spoken at this conference a couple of times before, mostly on camera-related topics. So yeah, with that, we'll get started. So when I first started working, a lot of the ISPs and cameras used to be external. So basically what that means is that you'd had an image sensor and some sort of a bus, some camera capture interface, and all of that would go to an image signal processor. And that image signal processor would be outside of the SoC. It would be integrated with the camera module. And that would get connected to a SoC or a host PC. Earlier days, it used to be parallel interface. A little bit later, maybe CSI-based cameras started appearing. But a lot of the ISP used to be outside, so all the functionality was built outside of the chip. So the SoC and host PC could use this. And I think this was perfect for V4L2, which is the original camera API for simple cameras. So I think you could have a V4L2 application. It's a very well-defined API. You'd have a lot of IOC tools for setting up cameras, setting up formats, streaming. And that application would interact with the V4L2 driver. And the V4L2 driver would be written for a particular hardware that supported all of these IOC tools. So here's a slide that sort of shows the V4L2 application flow, right? So there's APIs to query capabilities. You could set formats. Cameras could advertise multiple different formats. All that could get set. There are also APIs to request buffers. One shown here. You can query buffers, find out characteristics of the buffers, stride lengths, and things like that. And then you queue buffers, and then there's a streaming loop, right, where you'd start stream, and you'd constantly dequeue the buffers and queue and keep continuing within that, right, and stop stream, right? So this worked very well for simple cameras, especially cameras that were external to the SoC. It worked very well there. But then things started changing as the process node started getting better. You started getting internal ISPs, meaning that for cost reasons, right? Now SoCs are getting cheaper. So people started building just image sensors, which basically transmit in a format called Bayer. And that basically goes to the similar kind of camera interface, but around this time, maybe CSI2 became the more standard interface. And all of that would go into an ISP. And this ISP is now contained inside a SoC or a host PC, right? So actually, a lot of x86 PCs, motherboards, chipsets are also having ISPs built into them these days. So this evolution happened, right? And now let's take a look at a generic ISP that could be in one of these SoCs. So what that would look like, right? So there'll typically be an I2C controller to control the image sensor so that you can set up the image sensor, set various parameters, cause state transitions within the image sensor, right? So that's think of it as the control bus, whereas the data path is through MIPI CSI2, which would typically come into CSI D5 controller, and then pass through various levels of the ISP. A few of them listed here: black level correction, defective pixel correction, demosaic, color correction, and some oftentimes accompanied with scaling or color space conversion and a DMA to write out all of that to memory, right? And they also typically will also be present a statistics block, which will also have a DMA. And the purpose of this is to capture some image sensor statistics, which are fed into something known as 3A algorithms. That stands for autofocus, auto white balance, and auto exposure. And these algorithms will dynamically control the state of the sensor as well as the ISP. So sensor through the I2C and ISP via its registers, if it's an MMIO bus or a PCI bus, so via those registers. These corrections will be constantly made so that the entire camera subsystem is producing high-quality images. So now, this is the evolution of the hardware, and V4L2 had to keep up with that, right? So that's kind of when Media Controller came in, right? So now, I think the kernel developers realized that simple V4L2 would not work, but because now the hardware has gotten more complicated, a lot of these functionalities inside the SoC. So you need to have a kernel infrastructure to support all of that. So that's kind of what Media Controller does is it allows you to represent parts of this ISP camera as modular blocks, right? So in this diagram, all the green blocks are sub-devices, meaning that they have controls. They do have data, but they are normally internally piped to another block. The yellow blocks that you see are also much like the subdev. You can control them. They have parameters, but they will have a data path to memory. So there'll be so all the DMAs we saw in the previous diagram, they kind of get represented with the yellow boxes in this. So this can be generated using the media CTL tool print dot. So if you have a ISP that has represented as media pipeline, you could use that. Now, there's various ways to do it, right? Like the first representation is very, very modular, where each block of the ISP is represented. But you could consolidate some of these blocks together. For example, collection of these two, along with demosaic and color correction, could be bundled together as a single subdev and calling it the generic ISP. And then, two video nodes that come out of it. One is the scaler, and then the statistics, just like how we saw the hardware representation. So this is usually the choice of the implementer. How do we want to get it done? Both are valid ways of representing it. Now, oftentimes, even internal ISPs started getting more complicated. Like now you have more and more, like for example, what we saw previously was a single stream camera, which is very typical for your webcam, even like with traditional V4L2, but now multi-stream cameras started coming in. So this example shows almost a similar like previous pipeline, but now there's two outputs. There's two scaling, crop, and color space conversion as seen here, right? And you have the statistics just like earlier. And then two other blocks got added. There's a DWARP, mem to mem, and then there's a JPEG mem to mem. So some of these operations cannot be inlined along with the original ISP pipeline, so they function as distinct memory-to-memory blocks. And the V4L2 API has support for that as well. It's known as the V4L2 memory-to-memory or mem-to-mem. So let's look at the media graph representation of such a pipeline, right? So you'd have image sensor, CSI2, generic ISP, with two scalars now, one statistics node. And the two mem-to-mem pipelines are separate, right, shown here. So what would happen to build software for such a system? What you would do is you would kind of do the inline processing first, and then based on the use case, you'd pass it through either DWARP or JPEG. Or my colleague and I have a talk about this tomorrow, more details on this aspect of it. Feel free to visit that if you're interested. So now, there are certain ISPs, especially those in automotive domain, that are multi-context in nature, meaning that you might have multiple image sensors, and you want to time division multiplex that same ISP for all of those. I think it's very typical for automotive, because there may be 8 cameras around, and you're trying to get a stitched view, and you can do that with one ISP, but then that ISP is going to be multi-context. So what slight difference from previous diagram here. So your CSI controller can write out to DMA, and there may be multiple of these to represent the 4 or 8 cameras, and then your ISP can now will have a read DMA, which can read from you're basically separating CSI from the rest of the ISP, and then the rest of the ISP pipeline can be used in multi-context mode, where you just sort of use it in time division multiplexed fashion, right? So this kind of support for media graph multi-context doesn't yet exist, but I was fortunate enough to attend the libcamera workshop a couple of weeks ago, and over there it was brought up that there's some patch. It's more like a RFC at this point. Can cover some details about it. So this is basically enabling the multi-context approach to a media graph. So shown here with the black box. So the way it works, I haven't fully delved into it yet, but high level, this is what's happening, is that every time you open a media device, you get a context which is stored inside the file handle. And then each video device will also have its own V4L2 context, shown with the green circles here. And you basically, and there's some APIs to bind it. So the user space knows that, or can control like a given video device that's part of a media graph can actually now use that particular context, and it can operate on that. So there are some mechanisms given. This is not yet upstream, but patches have been posted, and I think it's been tried with Raspberry Pi. That's what the patch description states. Any questions so far? Any comments from the audience? Okay, I'll continue. I just, for the purposes of this presentation, I was also trying to look what's new since last LTS. So 612 has a bunch of rock chip VPU supported. That thing is for the codecs. I think a couple of improvements to OmniVision drivers, some CEC changes. I think more extensible parameters to Rockchip's ISP. 613 has some changes to UVC, yeah, and then a bunch of different ISPs have seen some extra support getting added. New ISPs also getting onboarded, like the MSM 8953. I think similar story for 614, like most of small feature additions, but mostly new drivers getting added from what I can see. Similar story for 615. I think there's a bunch of new camera subsystems. I think the SDM670 from Qualcomm, SM8550. Yeah, that's pretty much it. I think the next thing to discuss is libcamera. So because media controller, with its graph and all of its sub-devices and parts of it, it can get pretty complicated, and you need some sort of support in the user space. So that's when this project was started, libcamera. I think it started in 2019. It's still not in its 1.0. I think the current version is 0.5 something. There's a slide about it. So what's libcamera doing? So it's supposed to be the user space for media controller-based ISPs and devices, right? And it also has provision to support MEM-to-MEM post-processing converters, like we saw earlier, JPEG and DWARP or color space converters and things like that. So what it does is it provides a bunch of libraries, or you can say helper classes, and allows pipeline implementers, which is like basically the ISP driver writers and the middleware writers, to go and implement various functionality that adhere to a libcamera public API. So that's kind of what is seen over here, that there is a public API. And now there's a few other things that are being done by libcamera. So there are language bindings. So you can also do Python-based applications. But that is optional, so there's a native libcamera application is the most preferred method, and this might become the standard API. I think it's already on its way to becoming for Linux. There is also Android camera HAL emulation. That means that there's some code written by libcamera and managed by libcamera that will basically automatically use underlying pipeline handler and present an Android API to the users. So it's kind of helpful. So this makes it applicable to Android-based projects as well, right? If you do your work once in libcamera at a pipeline handler for ISP, you could use it for both Linux as well as Android by leveraging the Android HAL support. libcamera also includes a gstreamer plugin. So it is maintained out of tree inside the libcamera package, and it is also evolving rapidly. There's a slide talking about some of the new features added there. And it's pretty compatible with the rest of the gstreamer plugins. So you can use it just like any other gstreamer plugin, very, very compatible. But it's still maintained out of tree for now. I don't know whether it will move back into the gstreamer tree or remain to be here. So there's another interesting adapter called the V4L Compact. So this probably is only applicable to single stream cameras. So what it does is that if you have a binary application that already is using V4L2 API and you need to use that with libcamera, so you could use the V4L Compact layer. There's a bunch of environment variables to set up, and then it'll work like a regular USB camera, basically support all of those functionalities. So if your pipeline handler has all the necessary support, this should work. I have not tried it myself, but that's basically what V4L2 Compact is here for. So the other thing that I think I spoke about in the previous slide, that so there's a lot of helpers and support classes provided by libcamera, which make it easy for an ISP pipeline author to go and build their own pipeline handler. So this is kind of what's shown over here. So there's a pipeline handler, and there's a lot of device agnostic code here, which also uses these helpers. But the gray box shown here is supposed to be written by the ISP implementer, along with this other gray box, which is image processing algorithms. So this is the 3A algorithms I spoke about earlier, which leverages the statistics coming out of the ISP. And these both are implemented by the ISP implementers. One difference here is libcamera does allow the IPA, or the image processing algorithms, to be having a proprietary license. So the communication between pipeline handler and IPA is maintained over an IPC and DL open and those kinds of techniques. So the pipeline handler needs to be LGPL 2.1, but the image IPA can be a proprietary license. But they do require pipeline handler implementers to give a reference open source IPA as a part of once it gets onboarded into libcamera. And then there's a camera manager. This is used by the libcamera application. So this is because on a given system, there could be multiple cameras, and each of them will have their own pipeline handlers. So there's a camera manager to go iterate over all the different devices that are present on the system. And you could use that to decide which camera you want to operate on. And once you lock on a camera, then you have exclusive access to it. And the other applications could not use that at that point, right? So that's sort of what's happening here with libcamera. This is a list of all the different libcamera pipelines which are upstream. So you have ARM Mali C55, Intel IPU3. There's an NXP ISP, Raspberry Pi, a couple of versions, Rockchip RK3399, UVC video. Also, you could use them as traditional V4L2 API, but there's also a libcamera pipeline handler for UVC video devices. If you're migrating over to using libcamera API, that's helpful. And the IMX7, IPU6, and Allwinner Sun 6i, they all use a pipeline handler called Simple. So what that means is these are simple ISPs, mostly just having a camera controller. So all they can do is capture raw. And what that simple pipeline handler does is it allows you, it's a generic implementation for any ISP that is simple in nature. And then there's also extra provision there to link the raw with another optional mem-to-mem converter, right? So that's what simple says. So a lot of ISPs that are simple in nature are just not developing their own pipeline handlers. They just become compatible to the already existing simple pipeline handlers. And then there's a test driver that's known as the VMC, or Virtual Media Controller driver. So this is largely used for test use cases, VMC. So this is a good way to get, if you don't have a real system, if you're curious to try out libcamera, you can try that. You could also attach a USB camera and try libcamera. That also works well. So I said, yeah, the 0.5.1 is the latest. I think this is also updates which I picked up from the libcamera workshop a couple of weeks ago. And so they said that now the gstreamer plugin included in libcamera can actually, it exposes all the libcamera controls as gstreamer controls. And if you're on version 1.26 of gstreamer, so there are DRM format modifiers, and they can be used, that's the standard way to select compressed formats. For example, if you have YUV format, and then your hardware IP supports compression. So earlier days, I think people used to go and define a derivative of YUV compressed, but I think now the standard way of doing it is to use format modifiers. So it's YUV, but there's a way to indicate that it's compressed. So, and that awareness is now also coming to gstreamers from 1.26 onwards. There is actually a software ISP which has been included I think probably like a year ago. And so this is again for cameras that support RAW capture, and you could do a software-based ISP. It also comes with a software-based statistics and a software-based IPA. So I think this has been tested on some of the Qualcomm platforms. There was a talk about this in last year's EOSS. There's also a new tool called CamShark. I haven't tried it myself, but it seems like it's something that leverages the libcamera's Python bindings over SSH sort of an interface. And you could use it to debug various libcamera features, mostly focused around the IPA development. And if you can see from the screenshots there, you can capture, but you can also look at all the parameters as they're varying, and can be used for debugging. It's inspired by the Wireshark tool, which is used for network packet analyzing network packets. So similar concept. I have not tried this myself, but if anybody here has, please share your story if that's the case. Finally, I just wanted to talk about ROS. ROS stands for Robot Operating System. It's an open source. There is an open source version as well for ROS, and the latest version is ROS 2. I had some experience with ROS, that's why I brought this up. And ROS also has a way to deal with cameras. But before that, a very basic introduction to ROS. So it is a publish and subscribe framework. So you have a node, you have multiple nodes, and there's something called a topic, and you can send messages over topic. And then, once a publisher publishes a topic, all the subscribers get it, right? So that's sort of very simply speaking, what ROS does. There's also something called services, because the previous method, publish, subscribe, is one-to-many. So one publisher, multiple subscribers. But if you want some sort of one-to-one interaction, they have something called services. And ROS uses services for camera calibration. That's one of those places where ROS ROS service is being used, right? And here's a very simple slide just talking about how ROS camera would happen. So you'd have a camera publisher node. You could build that with libcamera, Android HAL, whatever BSP you have. You could build it with, you could refer to the API guide and write a publisher node. And once you publish an image over the ROS transport, multiple camera subscriber nodes could get it. The ROS also has ways to control parameters, which can again be advertised by this publisher node. So you could tie that down to V4L control or libcamera control if it's a libcamera-based implementation. So that way, subscriber nodes can influence the way the cameras operate, and runtime, you statically or runtime change parameters. So all of that is possible Yeah, I guess that's all I had in terms of slides, but if there's any other topics or anyone wants to share some experiences, there are 2 mics around here, so if anyone wants to. Yeah, sure, yeah.
The software ISP, I suppose that could probably run on the GPU if somebody coded up.
Yeah, actually, that's a good question. So the software ISP we spoke about earlier, I think which libcamera added support, there were some talks about implementing that on a GPU. Right now, it is on CPU because that was easier to do.
But nothing would preclude probably. Nothing would preclude probably the addition.
Yeah, you could definitely do it. Yeah. But I think there were some plans to have that available in the libcamera source itself. I don't know the status of it, but it'll probably appear sometime soon. Yeah, that's definitely doable. Any other questions, thoughts, comments? Anyone wants to share their story with cameras on Linux? I guess we could end early then if that's the case. Sonang, you have something to share? Okay. Cool, yeah, if there's no questions, I guess, yeah, we could end a little bit early. Thank you so much for being here.